So last week we had the saga of Reginald and Tony. And we were interested in why, and that would either be a 1 if the question was answered correctly, or 0 if it was answered incorrectly. And those values of 0 and 1 were assumed to come from a Bernoulli distribution with some sort of a parameter theta that was indexed by student. So we had theta 1 for Reginald and theta 2 for Tony. And then the prior was specified here as a beta distribution with two parameters, omega and kappa. And omega was something we were interested in because that was presumed to reflect the skill of the teacher. And to keep things simple, we fixed kappa. The prior for omega was assumed to be a relatively flat prior of beta 2,2. So, in this video, we're going to make things a little bit more complicated, as seen here in one of Krishke's figures. One thing we're going to do is we're going to add a hyperprior. So whereas earlier k was fixed, instead of fixing k, what we're going to say, it's going to have a hyperprior, kappa's going to have a hyperprior, and that's going to be a gamma distribution. So we're going to add hyperprior. And the second thing we're going to do is that when we went over this example, it was really just conceptual. And now when we do this, we're going to start to write some code. So that's just an overview of what we're going to do. So for this example, I'm going to forget about Tony and Reginald for a bit, and I'm going to go back to Krishke's idea of coins. So what we're going to have are 3 coins, A, B, and C, and they were flipped. And for coin A, 4 out of 8 were heads. For B, 6 out of 11, and for C, 5 over 10. So this is the heads, and this is the total. And we're going to view heads as being success, or 1, and the tails will be zeros. So there's a data. Our data are going to be implicitly indexed by the row number, and then they're going to be explicitly, at least we're going to have to figure out how to do this, we're going to have to somehow index them by the coin. So there's the data. And so if we look at our flow chart, what we're interested in is this pattern of y values, this pattern of 1s and 0s. And they're deemed to come from a Bernoulli distribution with some parameter theta, but theta is going to be indexed by coin. So there's going to be theta 1, represented in either written form or symbolic form, for coin A, theta 2 for coin B, theta 3 for coin C. So all these thetas, they're going to need a prior. And we're going to specify our prior in this way. And this prior is going to have these two parameters, omega, kappa. So let's first think about the prior for omega. That's going to be a relatively flat prior, d beta 1, 1. So I just want to spend just a moment and just reiterate what this really means. So it's a beta distribution. And here's the formula for the probability density of a beta distribution. So if we say we've got a beta 1, 1, what we can do is, this is the A parameter, this is the B parameter, we just substitute in 1, 1, 1, 1. Then what happens is we put in a value of theta, and every time we put in a value of theta, what gets returned is the probability density of theta, given that we parameterized A and B both is equal to 1. And if we do that, here's the value of theta. So we put theta in here, and we run theta between 0 and 1. The probability density of theta shown here is a constant. So essentially what this is telling us is that our prior idea about theta is we don't have a clue. A value of theta of 0 is just as good and probable as a value of 1. So that's how we're going to think about our hyperprior for the parameter omega. Now let's think about the hyperprior for kappa. That's going to be just a little bit trickier. Because if you think about what happens when we parameterize our beta distribution by omega and kappa, the way we express this is kappa minus 2. So whatever value in here goes in here has to be at least 2, so that when we subtract 2 from it, we get a positive number. So the way we're going to do that is a two-step process. We're going to create this variable kappa minus 2 that is assumed to arise from this gamma distribution. Rises from a distribution, hence the tilde. But then what we're going to do is we're going to use the equality. We're going to create a function that adds 2 to it. And the whole idea of having kappa minus 2 plus 2 is that if we put that right here, then once we subtract 2 from it, we'll have a value that's going to be positive. So now let's think about what the heck does this gamma 0.01, 0.01 mean? Well, this is the formula for a gamma distribution. And it's got these two parameters. S stands for shape, and R that stands for rate. And we specified that both of those are going to be 0.01. So we could put those things in here, each one of these S's and R's. We could put in as 0.01s, and then think about what's going to happen is for every value of kappa shoved in this formula, having specified S and R, those are given, what comes out the other end is the probability density of kappa. So if we actually set S and R as 0.01, what's the relationship between kappa that goes in here and the probability of kappa that's shown here? You can see that for most values of kappa, it's going to be a pretty flat line. So we can think about other values of shape and rate instead of these. And if you go on E-class, there'll be a program, prior distribution.R, that'll let you put in different S and R parameters and see what effect that has on the probability density kappa. So here's going back to shape 0.01, and you can see with that sort of a prior, K can essentially be anything. We know kappa has got to be positive, but it can be pretty much darn near anything. In contrast, if we were to say that shape was equal to 6.25 and the rate was equal to 1.25, then if we looked at the probability density kappa, it would be like this. So it seems to be peaked at around 50 or so. So in any event, that's just a very brief introduction to what in Krushky, he titles it as more realistic model. This is an introduction to this more realistic model that talks a little bit about the flow chart, and in the next video, we'll begin to see some of the code.